Alright guys, so today we're going to focus on different types of chemical structure. So firstly, let's quickly go over a few basic things again just to refresh our memory. So solids have fixed volumes and shapes, and generally the particles in a solid are arranged in a highly ordered pattern that maximizes electrostatic attractions and minimizes repulsion among the particles. This distinct highly ordered pattern is what we call a crystal, and we use a crystal lattice to describe their bonding pattern. So if you take like a lattice, I suppose, here I'll draw something. Yeah, I'll draw something just to. Okay, I need to here. Let's do that. So that's a highly ordered thing. That's a highly ordered system. As we can see here, it's nicely packed and it's clearly a bunch of dots. And we would call, let's use a different color right here. We would call this here the unit cell because it's the smallest sort of unit that builds up that giant structure. So that's sort of that. So yeah, that's really it. The sizes, electronic structures, and bonding of these things depends on the size and shape of the unit cell, and since there's so much variation, we don't tend to study it in that much detail. And there are some materials that have fixed volumes and shapes but have considerable disorder in their structures and don't have defined melting points. We call these amorphous solids. There are many types of solid. Here's the ones that we'll be taking a look at: ionic solids, moleculars, solids, network covalent structures, and metallic ones. So there are ions. You can read this chart for yourself, and I'll link the notes in the description like always, so you can read that at your own leisure. But for now, let's move on first to the first one, ionic solids. Ionic compounds consist of large three-dimensional crystalline structures, many cations and anions held together with ionic bonds. So ionic bonding is not just between an Na and a Cl, it's between a lattice of them. So this is sort of what we look at. So the big gray dots are chlorines and the small black dots are sodium. So this sodium here is bonded to 5 chlorines by an ionic bond. So this one, this one, this one, and this one. And then similarly, this sort of pattern repeats over and over again. It's actually 6, but since we cut the face off, there would be another Cl in front, but that's besides the point, I guess. This pattern is shown below. This isn't the only pattern for ionic solids. Bond lengths, angles, and all that stuff depends for different compounds, but the basic idea is that you have a small repeating unit cell that essentially builds up to build nice cubes and rectangles and all that stuff. You have these nice repeating units join up together to build these structures. Next we talk about molecular solids, and then we go on to discuss the topic of intermolecular forces. And intermolecular forces are the relatively weak forces of attractions between different molecules. For those of you that take biology, that would sort of be akin to emergent properties from one cell when you have an organ. Emergent properties is when the cells work together to do one thing, and I suppose similarly you could sort of think of it akin to that. The intermolecular forces are the results of emergent properties between each molecule and their intermolecular attractions to do something bigger than itself. Now, these weak forces of attractions generally occur between the nucleus of one atom and the electrons of another atom that is generally part of a different molecule. Although they're weak, they are very important. We're going to go from strongest to weakest in terms of intermolecular force types. The strongest is a hydrogen bond, which is the type of intermolecular forces that occur between polar molecules that contain a hydrogen attached to a highly small electronegative atom, which essentially translates to nitrogen, oxygen, fluorine, which classifies highly electronegative elements. Hydrogen bonding is the strongest intermolecular force. Essentially, you can just think of this as like a strong, very, very strong dipole-dipole force, which we will get to in a moment. Hydrogen is the least electronegative nonmetal, so when bonded to a very electronegative molecule, a nonmetal, the molecule would be very polar, and this difference in partial charges would generate strong forces of attraction. And hydrogen is very strong, a small atom with no core electrons, and therefore the hydrogen atom can get very close to the lone pair of another atom. So let's use water as an example. So as we can see here, there are covalent bonds in blue, and the intermolecular forces are in red. We know that according to the shape, this is actually polar, this is slightly positive, this is slightly negative, and since lone pairs are negative, and this is a slight positive charge, we know that there's going to be an electrostatic force of attraction to this lone pair. And then similar thing is true, and then you can think of this sort of effect builds up as you have more and more molecules, and then you get what is a glass of water at the very macroscopic scale. Water is interestingly, there's nothing really to note here, but that's sort of hydrogen bonding in a nutshell. These hydrogens must be directly attached to an N, an O, or an F. So do keep that in mind. Dipole-dipole forces are another type of intermolecular forces, and it essentially involves the opposite ends of polar molecules interacting with each other. So the slight positive end of the molecule will interact with the slight positive end of a different molecule, and since they have opposite charges, they will attract and come together, sort of more or less. They're not nearly as strong as intramolecular forces or forces within the molecules, maybe about 1% as strong as the chemical bonds that hold the atoms together. However, they're still worth noting because they do lead to some important macroscopic properties, such as what state is it in room temperature. Lastly, we go on to talking about induced dipole forces, which are a type of intermolecular forces involving the electrostatic attraction between a polar and a nonpolar thing. Generally, when you have a polar molecule, you can use the polarity of it to influence the electron distribution of another nonpolar thing. So say if there was an even dispersion of electrons here, you could actually change that, because if you input this negative charge here, the electrons on this side will generally tend to repel and push backward, and as a result you'll get a slight negative charge here and a slight positive charge here, just sort of as a result of that pushing of the electrons away caused by this partial negative charge here. So as you can see here, a temporary induced dipole is attracted to the permanent dipole, and once you remove that, it'll go back to normal, more or less. Oh, sorry, I need to take a sip of water. Now, what if we take this sort of effect to the extreme, to an extreme? Then we get something called London dispersion forces. So they're the type of intermolecular forces involving the electrostatic attraction between oppositely charged ends of a molecule that have become temporarily polar as a result of distorted electron distribution. So, oh, hang on.
Did you already get dinner or lunch? I mean, breakfast? Yeah.
Sorry about that. I was just talking with siblings. Regardless, so we get these things called induced dipole forces, and this is a result of just electrons naturally moving around randomly. Maybe in one instant in time, you'll get a distribution that causes the electrons to favor one side of the molecule as compared to the other side, and then this slight instant in time variation, this dipole that is instantaneously created will have an effect on the electron distribution in another atom, and then the other atom, and the other atom, and this sort of builds up, and then they have very, 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 very slight positive and negative charges that interact with each other. London dispersion forces occur with all molecules, polar and nonpolar, and then generally we refer to all the intermolecular forces except for hydrogen bonding. We call them collectively van der Waals forces. So here's sort of a table chart indicating the approximate energies of bonds and their forces. So as you can see here, ionic bonds are clearly the strongest, followed by covalent bonds, followed by dipole forces, which includes hydrogen bonding, and then induced dipole forces, and London dispersion forces. We can clearly see here that the stronger the bond is, the higher the more energy you need to break it. Nextly, we go on to discuss network covalent solids, which consists of lattice structure. You can think of it as like the lattice structure, but with covalent bonds rather than ionic bonds, and that's really all it is. There are a couple of specific examples you need to know of these network covalent structures. One of which I'll go over now, and another which I'll go over in the next video. But you're expected to know that silicon dioxide has a network covalent structure, as well as and diamond. Yeah, that's it. Um, yeah, they're just the ionic. They're like ionic lattices, but held together by covalent bonds. So as you can clearly see here, diamond. This is sort of what it looks like. As you can see here, it sort of takes the shape of a crystal lattice, but these are covalent bonds, and similarly with silicon dioxide. Lastly, we go on to discuss metals. The last sort of type of chemical structure is a metal. So metals tend to interact with this model called the electron C model. It's considered non-directional bonding, but that doesn't matter. Anyways, what do I mean by the electron C model? Since um, since the ionization energies in metals are fairly low, they tend to partially some of the electrons will generally just ionize. So it'll partially ionize. Some of the metal ions will ionize and create cations and anions, and then you have these nuclei, these positive nuclei, which are fixed, and the electrons can move around them, and the nuclei are attracted to the valence electrons. However, since the electrons are so excited enough to be out of the atom, they can be attracted to multiple nuclei, and sort of that's how it works. They get the lattice of cations are sort of attracted to the sea of delocalized valence electrons, sort of as how I would describe it. So you can see here sort of how it works. So these crystal lattices are fixed, however these electrons sort of just move around and vibe, if you will, all over. And yeah, that's more or less what it is. Metallic bonding is the electrostatic attraction between the lattice of positive electrons and these delocalized electrons caused by the ionization at room temperature. At room temperature, just the electrons. This is technically referred to as thermal excitation, and the electrons just have so much energy to ionize just free in a metal. You don't get this in a non-metal since they have very high ionization energies and high electronegativities, but with metals you actually get this effect because they are low. This bonding structure accounts for some of the properties that metals have, such as they are good electrical conductors since the electrons are free to move around and carry a charge. They could also be, they're also quite malleable since, it doesn't matter how you distort the sea of electrons, which are fairly easy to distort since the positive lattice will just sort of go to where the electrons are. So the application of force can make the cations move, but it doesn't break the bond since the valence electrons are highly delocalized. They'll just move around with it. Melting point trends for metals is that generally as you go up the alkali metals, as you go up a group, they tend to get higher and higher melting points because the metallic bonding between the cations and the anions is stronger because the cation radius is much smaller, and as we know from Coulomb's law, which I discussed in topic 3, the distance is much more important a factor than charge, and since decreasing the ionic radius decreases the distance between the charges, you get stronger electrostatic forces, which corresponds to higher melting points. And then similarly, as you go across a period, since the radii are similar, the higher charges cause for higher melting points, since they are stronger charges, and they have similar radii. An alloy is a material with metallic properties, which is a homogeneous mixture of at least one metallic element and either metallic or non-metallic elements. Most metallic materials are alloys, and there are many examples. You're expected to know a couple. I say steel, which is a mixture of carbon and iron. That is probably your easiest bet. But there's a whole list that you can memorize. Alloys are metallic because their properties are the same as the metals. However, by adding other metals or non-metals to it, you can augment the properties. So, say for example, carbon steel causes carbon steel is much stronger than just regular iron, and therefore that's why you use it. So you can use it to develop resistance to corrosion, wear, fatigue, and develop high-low metal. You can develop alloys that are temperature resistant, like they can withstand high or low temperatures, temperature extremes. Yes, and they tend to sort of average out the properties. Since they're a solution, they tend to average out the properties of each component of the mixture. So, yeah, thank you very much. Um, yeah, thank you very much.